The last LSD synthesis we looked at was a bit classical. Let's consider a more modern one from 2004. One of the starting materials is this nicotinic acid derivative, which was reacted with hydrogen peroxide to generate the N-oxide. This makes it reactive towards thionyl chloride. The oxygen attacks the sulfur, and a chloride ion is pushed away only to come and attack the ring from the other side. Electrons flow through and neutralize the nitrogen, and the paper postulates the next step was this concerted step to add another chloride. Sulfur dioxide leaves along with a molecule of HCl and substitutes a chlorine in this position. Methanol quenches the reaction and converts the acid chlorides to methyl esters. The next material was this 6-bromoindole. Potassium hydride and tert-butyl lithium were reacted to form a lithium-halogen exchange. This essentially behaves like an anion and can attack a substituted boron molecule into the empty p orbital. One of the O-butyl groups leaves, and once this more stable carbon-boron bond has been formed, the whole thing can be hydrolyzed with phosphoric acid to give this substituted boron. This was then combined with the nicotinic acid derivative in a Suzuki coupling, which is worth going over in some detail. The first step of any coupling reaction of this type is oxidative insertion. Palladium naught, which also has triphenylphosphine ligands, which I'll leave out because it makes the drawing crowded, inserts into the carbon-chlorine bond, and in the process is oxidized to palladium 2. Transmetallation comes next, where the boron and chloride leave. This is usually needs some base like potassium carbonate to do this. Anyway, another palladium-carbon bond is formed. And in the third step, the fragments are coupled by reductive elimination. The carbon-carbon bond is formed, palladium 2 leaves as palladium 0, thus being a catalytic reaction. The palladium 0 is reformed, and a carbon-carbon bond is the result. So now we've coupled the two fragments together, and the next bond we would like to form is here. That ester isn't really electrophilic enough to react with the indole system, so change in oxidation level is needed. Barium borohydride was first used to convert it to the alcohol. The barium chelates the nitrogen in the ring and allows a selective reduction to be performed, reducing one ester group only. Then the oxidation level needs to be converted again, this time up to an aldehyde, and manganese dioxide is selective for allylic and benzylic alcohol groups. If you wanted to draw a mechanism, it would probably be something like this. You start with manganese 4, rearrange some things, eventually some electrons flow into the manganese atom to reduce it to manganese 2, and we've also got an aldehyde. The indole is now happy to react with this, pushing the electrons up and then losing a proton to generate this. Borane was used for another reduction. The nitrogen probably again pushes out some intermediate like this, and then a hydride ion captures the product. After this, methyl iodide is used to alkylate the ring nitrogen, which then picks up a permanent positive charge and makes it much more reactive to sodium borohydride. The first reduction is here, and there's another reduction which needs to happen in this system. It'll be in equilibrium because the nitrogen has a lone pair and the whole thing is conjugated, so that can push around to the ester group. And then this intermediate can be trapped out by hydride reduction, leaving the ester in its enol form, which will then collapse down, protonating during the workup. And these two reductions have been the last step in the synthesis of methyl lysergate, and that's only one step away from lysergic acid.